Good evening. What a nightmare board, isn't it, eh? But it's not. I know some of you hate the numbers, but there is no choice. It's there. If you don't understand these numbers, how on earth can you understand about the sun, distance, diameters? If people struggle with this, right? People say, what's he talking about? What's he talking? He's very delusional. He's making no sense. I am going to make sense, okay? This is all about the diameters, right? It's about the diameter of the sun, not just the speed of light, but the reason a star radiates so far at absolute speed, its light, is because of the size of it, not the speed of the light, but the distance it will radiate. For example, we can come all the way down, but we're going to go smaller. We're going to start with a 5mm bulb. Like the lens was dirty. That's it. Ah, this phone's been smashed around so much. Oh, that's clear as. Right. Now this bulb, this is all about keeping things to scale, understanding how that works, right? Now, this light bulb, if I turn it on, its light is going to radiate a certain distance, right? And it will stop. And that will happen, bang, like that. It's as far as it's going to go. The light is, if you put your hand over on that far fence, if I'm outside, you might just get a shadow on the fence, kind of thing. But the further away it is from the hand, the less chance of it being powerful enough to create a shadow, like the stars. The stars are too far away to put your hand out like that and get a shadow on the ground because the stars radiate in light. The sun, yeah, but the stars are too far away. Now again, this bulb, 5 centimeters in diameter. Yeah, just over 5, call it 5. I go like this, bang! Its light has radiated as far as it's going to go in an instant. Somebody looking at this, I think we call it 5Ks, but it's probably further. They'll see it at the same time as I see it. If I've got somebody looking over there, 5Ks away, and I'm looking at it and I go like this, we both see it at the same time. Whether you like to accept this or not, we both see this light at the same time. Anybody who was in visual range, anybody who can see this light bulb, who's close enough to see this light bulb, will see it at the same time as somebody who's like me, right next to it, somebody who's 50 meters, 200 meters, 2 kilometers, 4 kilometers. Anybody who can see this light bulb will see it at the exact same time. But people 2, 4, 6, 8, 10, up to 50 Ks away. We know it's not going to reach 50. Go like this. Now, everybody who was within range of seeing this light bulb would have seen it, bang, as soon as I turned it on. Bang! Everybody, all the way down to 8, 9, 10 Ks, as far as it will radiate. Everybody's going to see it at the exact same time. There is going to be no delay. It's not like I'm going to see it first, and then the guy at 1 Ks, and then the guy at 2 Ks, and then the guy at 3 Ks is going to see it later on. And that's what they're telling people. It's wrong. The bigger the light source, right, the further the light will radiate at absolute speed. If I pump this up to 30 centimeters in diameter, and it was a bulb and I turned it on, bang, 30 centimeters, so that's 6 times the amount of this, like a ball, right? That big. Now, it's not going to be just 5Ks over the river, is it? If I have something that's as bright as this, same wattage or whatever, but it's got 30 centimeters, like diameter of 30 centimeters, and I go, bang, people are going to see it at 15, 20 kilometers, aren't they, on a dark night? But they're going to see it, bang, the same as with the bulb, when it was a 5 centimeter diameter bulb. People at 5, 6Ks, they're going to see it as soon as I turn it on. If it's 30 centimeter diameter, that's 5 times as far. We could call it 30Ks easily. If this was the size of a soccer ball, bang! People who are looking in the direction of the 30 centimeter diameter soccer ball bulb will see it the minute, the second my fingers move, like that. And boom, there's not going to be some kind of delay, right? And then we get bigger again. Let's say it's a 10 meter freaking sun, right? Now we're talking, I don't know what we've gone from. Look, it doesn't matter because we're going to do this on the board anyway. But what I'm saying is, the bigger the light source gets, it's always going to radiate at absolute speed. Bang, everywhere, right? Always. But what they have people thinking is when it gets to a light source of 299,792 kilometers, should recognize this number, I hope, that's the number for the speed of light. So now all of a sudden, we have a star that has a diameter of 299,792 Ks, right? The speed of light is 299,792 kilometers per second. So straight away, at this size, now it's going to take this star that has that diameter 1 second to radiate its own light the distance of its own diameter. All right? So let's go down. So about that'll do. Right, so that's 1 sun diameter. Now, because its diameter is the same in kilometers as the speed of light, it would now take that star 1 second to radiate its own light the distance of its own diameter, because that is the speed of light. 1 second. On your marks, get set, go. So, not as slow as the sun in relation to themselves, but 1, 2, 3, go. At 1 second. But the star, that size, 299,792 kilometers, will still radiate its light like this. Just that now, the distance that it can be seen, long way, right? This is the speed of light being finite. It's illogical. It doesn't make sense. It is highly illogical. especially when we get to the diameter of the actual sun. If that was 1,390,000 kilometers in diameter, 4.6 seconds for a freaking star. It's insane. Not as insane as UY Scuti. 2.377 billion kilometers in diameter. Because it's so big, it takes UY Scuti 2 hours and 12 minutes at the speed of light to radiate its own light the distance of its own diameter. It's a load of rubbish, and it is about common sense. It really is. The more you just think about it. Now, this is about, now I've done that bit, we're going to keep things to scale. We're going to keep things to the correct, in the correct proportions. Sun, the distance from the sun to Earth, and Earth's diameter. So all three, sun, sun diameter, distance to Earth, and Earth's diameter. No Daisy the cow. As much as you wanted to be here, I just had to put my foot down. I really did. Now, and this number, we're going to come to this number at the end. Let's see if I'd be one of those things, those quiz things. Oh, can anybody, if anybody guesses what that number is by the end of the show, we'll give y'all a free car, okay? Like Oprah Winfrey. Everybody gets a fucking car, okay? If anybody gets it in the audience today, everybody gets a fucking car, okay? So you just gotta, what is that number, okay? That'll be the future when I'm a highly rated science buster, when I'm finally taken seriously, all right? Everybody will get a car in the audience. So why don't you help me? Nudge me along, okay? Now, what we have here, remember, I know you guys have a lot of trouble with the keeping to scale thing. There are 108 suns in between planet Earth, us, and the sun. There are 108 suns. We know this because we divide the distance, 150 million kilometers, by the sun's diameter, 1,390,000, and we get 108. So, knowing this, any time that we want to do a diagram, a working diagram of the sun, distance, and Earth, or we can make the sun whatever diameter we want, and all we do is multiply that diameter by 108, and it will give the distance to Earth. It doesn't matter what size it is. If you multiply it by 108, because there are 108 suns, this is their numbers, okay? And I'm doing this as if it's around Earth, because that's kind of what I know. But flat earthers, you know the score. I'm not saying it's either way. I'm explaining it as I best know how to, okay? Now, 108 sun diameters in between the sun and Earth. If I have a 1 meter diameter sun that I'm playing with, then the distance to the Earth will be 108 meters. Doesn't matter what size sun it is, 108. You multiply it by 108 and that is the correct ratio, okay? Now, with that, when we have this sun, like we're going to use a 5mm bulb, to find Earth's diameter, which is purely a reference. But it's handy to have the sun, the diameter of the sun, you know what it is, you know the exact distance. It's kind of good to know what Earth's diameter would be. In this case, it's 45 micrometers. There are 1,000 micrometers in a millimeter. 1,000 micrometers in a millimeter. And Earth, if the sun were a 5mm light bulb, half a centimeter, If the sun were that small, the distance to planet Earth would be 54 centimeters. That's the 150 kilometers, 150 million kilometers. It comes all the way down to 54 centimeters. And planet Earth ends up as a speck of dust, 45 micrometers, which means there are 21, 22 Earths in a millimeter, right? We are talking small, right? Now, if I turn this bulb on, we've done this before, right? We're going to turn the 5mm bulb on, bang. Now, the distance to Earth is that. That is perfectly to scale. The proportions are bang on the money. The light, as you can see, obviously it's going to go as far as it's going to radiate, like that. And anybody who's at a distance looking this way when I turn it on will see it. As soon as I put it on. As soon as I put it on, they'll see it, won't they? If they're too far away and they just don't even see it, then they're out of range. They'll never see it, right? Light won't travel towards them. Ah, yeah, but you're talking just a light bulb. It doesn't matter. As things get bigger, they don't change their behaviour. This is kind of a point that I'm trying to make as well. We don't have these bulbs going boom, radiating thousands of its diameters as soon as it turns on, because it is thousands. 5Ks is 100,000, because this is 5 centimeters. Multiply it by 100,000 and we have ourselves 5 kilometers. If you're 5 kilometers away from this bulb and I turn it on, you're going to see it straight as soon as I hit the switch. You'll see it at the same time as me. Now, as the light source gets bigger in diameter, what's going to happen? The amount of diameters that these things are radiating, it's tens of thousands, 100,000s in a heartbeat as soon as I switch on. But you guys, they've told you that as the light source gets bigger and bigger and bigger and bigger and bigger and bigger and finally gets to a diameter of the sun, which is 1,390,000 kilometers, we divide that number by the speed of light, and all of a sudden it's taking 4.6 seconds to radiate its own light the distance of its diameter because of the speed of light. It's almost like an internal battle, isn't it, between science and the speed of light? Because we know that for something to take 4.6 seconds to radiate its light, the distance, it's like an ice cube in the heat. You'd expect it to melt, and maybe one of its diameters every 4.6 seconds if the sun is beating down on it, but not a star. The bigger and more powerful something gets, the further it will radiate its light at absolute speed. Surely this is, I'm not going to say obvious, but I'm hoping, well, I know some people are starting to break through the cloud of dust, but we need everyone to break through the cloud of dust. This speed of light is Mickey Mouse. It's illogical. It's highly illogical. Can you picture a time? Could you ever imagine this bulb taking 8 minutes and 20 seconds for its light to reach, for its light to travel 108 diameters of itself to there? 8 minutes and 20 seconds, because each of those 5mm bulbs, the sun at its size takes 4.6 seconds to radiate each diameter. Now, obviously it's not going to happen down here when we watch this bulb, even though it's all to scale. But that is what they are telling you is happening up there with the sun. It's taking 4.6 seconds to radiate its light the distance of its diameter. Guys, bang, nothing, a star, a fucking star. You think if it takes 8 minutes and 20 seconds for it to radiate its light to here, 108 diameters. 108 diameters of this, what was it? 5.4 meters. 5 centimeters multiplied by 108 is 5 meters and 40, no, it's not 5.4, it's 5 meters and 20 centimeters, right? 5 meters and 20 centimeters. That would be the distance to planet Earth. 108 diameters, 5 meters and 20 centimeters. Probably over to that. Look, boom, boom. But as it gets bigger and bigger and bigger, and it becomes a sun, all of a sudden it's like, oh, such an effort to radiate my light. Oh, but 1, 2, so it's ridiculous. More powerful, bigger. But no, even though it's more powerful, bigger, brighter, everything up, it's a snail when you compare it to a smaller version of its previous self. It is ridiculous. It is 100% ridiculous. You know what? I was going to do this, but I might sack this now because everything's going to get... I don't want to overload people with numbers, but let's just do one more. This right here is a thing on its own. You could ignore all of this, it's on the board, and just focus on this square. Again, it's about diameters and understanding that when you keep things to scale, you'd expect certain things to happen. Only a lack of common sense or science telling me that it didn't care about my common sense would make me freaking believe what they're telling us. Now, the moon has a diameter of 3,476 kilometers. This is what they tell us, okay? I can only use their numbers. If the moon were the sun, the moon that we have in the sky, if it were the sun with a diameter of 3,476 kilometers, if we wanted the distance to Earth from that moon, a sun, it's making out to be a sun, we multiply it by 108. Right, sun, we get the distance to Earth, 108. So we multiply it by 108 and we get 375,408 kilometers, right? It's the same as 5 centimeter bulb, 54 centimeters. Yeah. A 5 millimeter bulb, 54 centimeters. A 5 centimeter bulb, 54 meters. Sorry. No, 5.4 meters. Look, you know what I'm saying? Look, they've got numbers. Bang, 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 bang. Right. So we have a moon, which is the sun, and it has a diameter of what the moon does. The distance to a planet Earth would be 375,408 kilometers. It just so happens that the average distance, why isn't that up there, from the moon to us is 380,000 kilometers, right? So let's just put that down there, right? 380,000 kilometers. So that's the average distance from the moon to us. Now, this is a really cool coincidence, right? Again, this is something that I bumped into on my travels doing this, right? I never saw this come from anywhere else. Same as the 4.6 seconds for the sun to radiate its light, the distance of its own diameter. I'd never heard of it before until I was messing around with the numbers. You know something is wrong. So, from the beginning, the moon, it is our sun, right? The moon is our sun. It has a diameter of 3,476 k's, which it does. We want the distance, if that were the sun. How do we find the distance to an Earth? We multiply it by 108. That gives us 375,408 k's. 5,000 kilometers out of the actual distance that we are from the moon. It's perfect. The only thing that would change is planet Earth would shrink to a diameter of just 32 kilometers, right? The reason for this, we know that there are 109 planet Earth diameters in the sun's diameter, right? So to get Earth's diameter, we divide the moon's diameter by 109. Right? It's the only two equations there are. We multiply the moon's diameter by 108 to get the distance to Earth, and then we divide the moon's diameter by 109 to get Earth's diameter, because there are 109 Earths in the sun's diameter. 31.8, I call it 32. So here's the thing. This is keeping everything like this, in proportion to scale. A 5mm bulb, the distance to Earth would be 54 centimeters, and Earth would have a diameter of 45 micrometers, right? That is the exact same ratio as a star, the sun, having a diameter of 1,390,000 kilometers, the distance to Earth being 150 million kilometers, and planet Earth having a diameter of 12,742 kilometers. Everything is perfectly to scale, right? Here, because everything is to scale, you would expect, if the same thing, if we want to see the same thing down here that is happening up there, it's going to take 8 minutes and 20 seconds for the sun's light to reach planet Earth. This bulb is going to radiate its light at a rate of one of its diameters every 4.6 seconds, because that is what they're telling you the sun does. So that would happen down here. That's what we want to see. But we know for a fact that when we turn this bulb on, 4.6 seconds per diameter. We're going to sit here for 8 minutes and 20 seconds as the light reaches a planet Earth. Give me a break. But when things get bigger and more powerful, oh, they do slow down in relation to their previous self, which is a load of rubbish. It's a load of rubbish. It's got that pi angle to it as well, right? It's a mathematical constant, a sphere. Why on earth would a sphere, as it gets bigger and more powerful, suddenly slow down its rate of radiating light in relation to a smaller version, a version of itself, a smaller version, like this bulb It's a light sphere. It's a spherical light source. Bang! 100,000 diameters, 5 kilometers. Bang, in a second. A star, the sun, if it does this, no, it's rubbish. The sun turned on from off. Poof! What was it, 139 billion kilometers? Well, yeah, because we called this 100,000, so 5 kilometers. It's a very, very, very modest estimate. 1,390,000 kilometers times 100,000, I think it was 139 billion. So, what they are mesmerizing people with is bullshit. A star, a light source, a spherical light source, will not slow its rate of radiating light to somewhere. It's not going to get slower as it gets bigger, is it? Why would it? Oh, because of the speed of light, and we're standing on the shoulders of giants. Einstein, Newton, all of the scientists, they've tested it. LiDAR, GPS, rubbish, rubbish, rubbish. During a solar eclipse, there is no light delay. The sun is directly behind the moon, radiating light like this. Bang! Bang! That's why there's no delay. That's why there never is a delay. You won't ever get a delay from light. Shadow, look. It doesn't matter how far away the light is. If the light is reaching somewhere and a shadow can be cast, the reason that the light is reaching and is casting a shadow of something is because it's powerful enough, it's close enough. It's not gonna cast a shadow, something casts a shadow 8 minutes and 20 seconds later, and the light finally gets there. What a load of rubbish. It wouldn't line up. We've been through this 1 billion times, not 1 billion, lots of, at least 100. There is no delay between the sun's light getting to the moon and us. There's just no delay. If it's on us. If it's off, it's dark everywhere. There is no delay. It's ridiculous, guys. It's ridiculous. That 278 billion. I just, for some reason, wanted to know how many. So I divided the sun's diameter by 1,390,000 divided by 5 millimeters, and there's 278 billion of them. So the sun's diameter, if their numbers are correct, this is 5 millimeters, we need 278 billion of them. That's how big the sun is. That's the diameter of the sun. So basically, I didn't go this far. I got, if we multiply 278 billion by 54 centimeters, we should get close to 150 million kilometers. Alexa, what is 278 billion multiplied by 54?
278 billion times 54 is approximately 15.01 trillion.
15? It is. Alexa, what is 278 billion multiplied by 54 centimeters?
278 billion times 54 centimetres is 150.12
There
million
you go.
kilometres.
I hadn't done it. And Earth should be close to 12,742 kilometres. Alexa, what is 278 billion multiplied by 44 micrometers?
217 billion
Alexa.
times 40.
Are you listening to me? Alexa, are you listening to me? Alexa, are you listening to me?
I'm designed to protect your privacy. On Echo devices, you'll always know when Alexa is listening to your request and sending it to Amazon's secure cloud. Just look for the blue light indicator or listen for an audio tone. Learn more by visiting amazon.com/Alexa privacy.
Alexa, what is 278 billion multiplied by 45 micrometers?
Sorry, I didn't get that. 278 billion times what?
45 micrometers.
278 billion times 45 micrometers is 12,510 kilometers.
12,510. All right. 12,510. The Earth's diameter is 12,742. And the reason for that slight difference and the difference with 150 million is because the rounding down to it might have been 44.111 micrometers. I just call it. So there you go. I hadn't done that. I hadn't done that extra step. So basically, it's 278 billion to 1. That's the scale. A 5mm bulb is 278 billion to 1 scale with the real sun. Let's stay at another 2 points. That was a good shot from here. Look, you can paint this. You can keep digging your heels in. Oh no, Einstein, shoulders of giants. You can. Good on yous. But everything, every single calculation, everything that you ever look at, the eclipse, Proxima Centauri, everything, there is no indication anywhere of finite light travelling at Mickey Mouse 299,792 kilometers per second. Light is absolute. It just is. The filming of that light in the bottle, what a load of rubbish. Do it live, show us, do it properly. Can't be done. It's the lies, they're everywhere. Right, I'm going to call it there. I bet that's gone well over the half an hour. To me, it's just so obvious. There's no need to go and do that one. It was just about getting bigger and bigger and bigger and bigger. I think we kind of covered the absurdity. As something gets bigger, it doesn't slow down. It's like me. I can, let's say for example, I can kick a ball 30 meters. Bang! 30 meters, right? Increase my size by 10. So I'm now, instead of 1.8 meters or whatever, I'm 18 meters high. The ball is now from 30 centimeters to 3 meters. Everything, if everything stays in proportion, everything stays as it was when I'm this size, when I kick that ball, it's going to travel not 30 meters, it's going to travel 300. We multiplied it by 10. If my size increases by 10-fold, everything, to keep things to scale, everything must increase by the same amount. The ball doesn't have to increase by the same amount of distance, but why wouldn't it? If everything has times 10 and stayed the same, bang! So we times 10 again. I've gone from 18 meters to 180. The ball is now going to go from 300 meters or whatever it was to 30 kilometers. And the size of it will have gone from 30 centimeters to 3 meters to a 30-meter ball. Everything just grows big. So when I kick that ball now, bam! It's still going to go the equivalent of 30 meters, but times 10 times 10 to the power 10 or whatever that. Well, you know what I'm saying. But if I keep getting bigger and bigger to the stage where I'm 1 million kilometers tall, the ball is going to travel, bang! What? Times, at 1.8 it was 30 meters, at 1 million it would be, but you know what I'm saying? It's going to travel, everything's going to stay in proportion. So why doesn't the sun, why doesn't what we see down here, bang, all of those diameters, but no, the sun, but boo. It's ridiculous, guys. Honestly, it's absolutely ridiculous. All right, 41. Jeez. All right, peeps.